So I'll just tell you a little bit about myself. My name's Dave Marsh. I've been a flat earther for about coming up to 2 years, and I've probably been doing my own research and experiments probably for just under a year and a half. I've concentrated mostly on the moon because I've always been fascinated by the moon. So the majority of my research has been based on that. And I don't know if you've ever seen my moon race series, but what I did, I've created a series of presentations called Moon Race, where what I do basically, I record the moon with my Nikon Coolpix when it's on the tropics and the equator, and I basically race the moon against each other to see if there's a change in speed. So what I'll do now, I'll just present this to you, and I'll show you exactly what I mean. So I can just share the screen now, can't I?
Yes, you should be able to.
But what I did, I had a few debates with Darren Nesbitt in regards to the square model and the circle model. At the time, I was supporting the circle model, so I derived these experiments where I record the moon when it's on the Tropic of Cancer, then obviously I record it when it's on the equator, and then I record it when it's on the Tropic of Capricorn. What you would expect on the circle model is that as the moon gets southern declination, you would expect it to speed up to cover that more ground, as to speak. If not, then at least it would need to explain how places like Ushuaia in southern Argentina get 18 plus hours daylight on their summer solstice. So I derived this video where what I did basically, I set my camera up with a compass, and I record the moon on 3 separate occasions at my zenith. Before I did it, not at zenith, but I've learned as I've gone through this experiment. When the moon's close to me on the Tropic of Cancer, to take a snapshot of the moon, there it is at 187 degrees, just past zenith. I take a snapshot with time and date to match that up. Now, if you look at the reading, just say, you'll see it's at 183 with an altitude of 55.
Yeah.
Now, if you look at my own readings, you'll see I'm a little bit at 187 at 56. You know what I mean? I'm not quite in the center, but you can see I'm pretty close to what I'm trying to do, like.
Sure.
So I've always backed up my readings with time and date, mooncalc or stellarium. I used stellarium and mooncalc for this one. So then a week later, when the moon's over the equator, not many people know that the moon crosses the equator 26 times a year compared to the sun only doing twice. So then again, when it's on the equator, as you can see, it's traveling in a perfectly straight line. It was actually a full moon. And then again, I've got my readings there, look, at 182, and then I take a snapshot with stellarium. And that's on the following night, that is, because what I've done as well, not only have I got my own readings, but I've actually gone on to time and date and took the meridian passing for when the moon to occupy the same spot the following night, and measured that gap between nights, you know what I mean?
Yes.
So if the time span's longer, then obviously the moon's slowing down, and if it's shorter, it's speeding up, which which you'll find pretty interesting in a minute. So then what I did, I basically raced the moon against each other on 3 occasions. So you've got the equator on the big screen, you've got the Tropic of Cancer on the bottom left, and you've got the Tropic of Capricorn. And what I did, to save time, I record them all at ×4, but they are all at their relative speeds. I have got the original footage as well on my camera still, so I've kept these, and basically race them against each other. I learned quite a few things since I started working on Moon Race 3, which I'm working on at the moment. As you can see, it was overexposed as it enters the frame. I've managed to sort that out now, so when the moon comes on frame, it looks like the moon and not like the sun.
Right,
So like I say, I basically racing against each other, and what I noticed were that when the moon was leaving the Tropic of Cancer and going towards the equator, it was speeding up. Not only was it speeding up, when I went on to time and date and looked at the meridian passing on that day, the time was around about 24 hours 42 minutes. Yet on the Tropic of Cancer and the Tropic of Capricorn, it was around about 24 hours 50 minutes. So it's actually, what I'm observing in reality is actually matching up with that meridian passing on time and day. And I've got this on 9 occasions, and I'm going to be using 6 of my own observations in my next video. I couldn't use my first 3 because I did it at a different zoom level, but my last 6 observations are all in the same zoom from the same location in our back garden. And here, what I try to do now, I try to explain why the moon's doing this. And I just put this little speech here, this little quote from Tesla about how scientists have substituted mathematics for experiments, kind of thing.
Yes.
So this image here, I come to the conclusion about it over a year ago, maybe even longer, that the sun and moon, especially the moon from my point of view, is more likely a projection. Yeah, what we're actually seeing from our perspective is not the actual image of the moon, it's a projected image. And you see the bright spot in the corner, that is actually the moon overexposed. And what it did, it actually produced a glare, a projection glare on the camera, which created the moon.
Right.
I've got quite a few of these images, and this is what and I don't know if you've seen Steve Torrance and Mike Kavanaugh's latest video about the electromagnetic Earth, and they've come to the same conclusion about the sun being a projection. So it may be worth checking that out as well.
Yeah, I'm at this point tending to agree with that line of thinking, for sure.
Yeah. So then what I did, I just put my theory on it. So I said basically the electromagnetic ether is a luminescent fluid substance for the propagation or the carrier of light, and it's a constant state of constant flux of vortex motion, and it carries all the heavenly bodies according to their altitude and their varying densities, and it's made up of 2 vortices. Not many people know this when they're stuck on a one-pole model, but it's pretty clear to see that there's 2 vortices, just like there is on a magnet, or 2 fields. So you've got one in the north, which is mine from the top, and the one in the opposite direction from the south, which was captured by my friend Paul Kofo. And what I did now, I captured some star trails with the moon in the actual video to show that when the moon's above the celestial equator in the northern hemisphere, it travels around the northern vortex, but when it's on the celestial equator, it'll basically travel in a straight line, and then when it's actually below, on the Tropic of Capricorn, it will follow that southern vortex.
Yeah.
And there you can see, like, and this is just like a little snapshot of where you can see the northern celestial and the southern.
Very nice.
So that's where I got to in Moonrace 2 video. I basically said then, so when the moon is above the celestial equator in the north, around the Tropic of Cancer, it's circling the northern vortex, and when the moon passes the celestial equator, it will pick up on the ethereal currents in the opposing vortex. And when the moon is below the celestial equator around the Tropic of Capricorn, it's circling in the opposite direction in the southern vortex. Some people might not be able to get their head around that, but what I think you need to do, from what I learned, is you need to learn to separate the celestial from the terrestrial. Yeah, a lot of people are relating the 2 poles, which I refer to as the celestial poles, as geographical poles. I'm referring to celestial poles, and this is where my research has led me to electromagnetism as well. Even though I'm not I don't claim to know everything about electromagnetism, I've basically just scratched the surface of it. I'm like a lot of flat earthers, I learn as I go, you know what I mean? It's
of course.
I didn't know nothing before I come to this. So that's where I got out with that video. So what I did then, thought to myself, I wonder if NASA has a working model of the moon around the Earth. And luckily, I found a model which is based on NASA's lunar reconnaissance orbiter visualization. And what this does, shows you the distance from the moon from the Earth, obviously when it's to 28 Earths away, it's closest at perigee, and then obviously as it moves further away, it moves away to apogee at its furthest point. Now, if you know anything about elliptical planetary orbits, which was what Kepler, one of his laws were, the planetary motion, were that planets will travel around the sun in an elliptical orbit, and what they'll do, they'll speed up at the closest point at perigee, and they'll slow down at their obviously furthest point away at apogee.
Yeah.
Now, interestingly, because I've captured the moon through March, where we're coming up to it now, yeah, on the March the 6th.
Mm-hmm.
This was my first observation. Yeah, if you saw that first moon what I had on that video I just showed you there, and you see the moon's in the exact same position. What I noticed were, this is when the moon was, on my observations, and according to that meridian passing on time and day, was when the moon was at one of its slowest parts of its cycle, from a flat earther's perspective. But as we got to near the full moon, which I think was on the 12th or the 13th, yeah, it was round about there. Now, this is where I recorded the moon at its fastest, and I think it took 24 hours 42 minutes on the meridian passing, and it also crossed my screen faster. So what I'm shooting in reality is matching up with what's happening on time and date with that meridian passing. My observation on this day, that meridian passing time is shorter, which tells me that the moon is speeding up in its cycle. Now if you look at the moon here, you see this little moon, it's actually heading away towards apogee. So how can that be speeding up in its cycle when I can prove, back to the time and day, that the moon only speeds up when it's on the equator? Yeah. And this is not just a one-off thing. As you can see, it's heading towards apogee. It should start speeding up as it passes that point of apogee, and then it heads towards perigee like it is now. This is when it should speed up in its cycle, as it's getting closer to the spinning ball kind of thing. Yeah. So I can prove that beyond the shadow of a doubt that that's not happening. And to back up my claims, what I've done, I've actually measured that meridian passing for a full year when the moon's on the Tropic of Cancer, the equator, Tropic of Capricorn. And what I've noticed is, as you'll see, when the moon is on the Cancer, it slows down. As it heads to the equator, but as it heads back to Capricorn, it slows down again. But the strange thing is, when it leaves Capricorn and goes back to Cancer, it stays at relatively the same speed until it gets back to that point when it's heading towards the equator again, and it speeds up. Now, this is consistent. You can go 10 years into the future or 10 years in the past, and it will always speed up at that point. Now interestingly, if you highlight them all, what you'll notice is over the year, if you look down there, you'll see an average of 50.89, and we all know that the mean time of the moon, it takes 24 hours 50 minutes. Now these readings work out perfectly with that. So what I did, I went to my March observation, moon race video, and I measured it every single day. And as you can see from my first observation, the moon's at its slowest, and as it speeds up, when it gets towards the equator, you see how it's speeding up on the 11th and 12th. Yeah. You can't see the 12th actually because it didn't cross the meridian on that night, but you can see it speeds up. Now you're probably thinking, yeah, but this is only from your perspective, isn't it? What about if you went to a different place? So I went on the exact opposite latitude to a place called Ushuaia in Argentina, which is on the 54th south latitude. And guess what? Even from their perspective, when it heads towards the equator, it speeds up as well. Now these are all time and date meridian passes, what I've measured myself and calculated throughout my observation. And then what I did, I went a step further. I went to a place in Indonesia called Pontianak, and guess what? On the equator, it speeds up again from their perspective. Yeah.
Wow.
So I can prove beyond a shadow of doubt that my observations are matching up with the meridian passing. So when the moon's speeding up from my perspective, it's speeding up no matter where you are on the plane. Yeah. And also what I've started building now, because I did some more moon race observations in August to September, I've started building my observations up around there. And I'll give you a little demonstration of how I actually do it. Where's one? Yeah, this one will be alright. This is a real-time one. So all I do, moon off my screen. It's not the easiest thing to do.
No.
As you know, as you can see now, look, it doesn't overexpose as it comes on screen, because as I've gone through these observation experiments, I've learned, you know what I mean? I've learned as I go. And
sure,
you set for an hour to get the moon in that position. I can do it in like 5 minutes now when I need to do it, you know what I mean? So,
nice.
So I've recorded the moon 3 times again, but this time, instead of going from the Tropic of Cancer to the equator to Tropic of Capricorn, where I saw that speed up, I did it from the Tropic of Capricorn this time. Yeah, and I came back. And what I did a quick calculation. I basically timed this moon, and I checked it with that meridian passing, and I think it took 24 hours, and I think it was something like 52 minutes from my first observation. When I went to my other reading on the equator, yeah, when it just speeded up slightly, the meridian passing was 1 minute quicker then as well. And then when I went to my third observation, which seemed to take a lifetime for it to get from one end of my screen to the other, when it was on the it took like nearly 7 minutes. But when I looked at the meridian passing there, guess what? It took nearly 24 hours and 58 minutes. So when I'm shooting the moon in reality, where it's speeding up from my perspective, or wherever you want to shoot it from, it's matching up with what I'm doing on time and date. So what I'm going to do, I'm going to use the scientific method, because I've got all the information and data and tools I need to debunk NASA's lunar reconnaissance orbiter, to prove that distance they use in their model is pure math, and also that 5-degree inclination they use is math as well. Because we know as flat earthers, when a celestial object is closer to the observer, it will appear higher in the sky. But according to the heliocentric model, the reason why the moon appears high on its northern path is because of that 5-degree inclination. It's a little bit like the 23.4 degree tilt of the Earth, you know what I mean? When it's tilted, yeah, it's same with the moon. So when the moon's high in the sky, they say it's this inclination, but it isn't. It's because it's closer. In my observations, and I can prove, when I put it all together, I'm still in the process of doing that, that the distances, they're just using math, and that inclination is just math as well. Don't get me wrong, their phases are spot on, and then some of the other stuff, but when it comes down to that distance away from the Earth, it's all math.
Sure.
And,
yeah.
And that's where I'm at with that.
That's very cool. Of course, they'd have to present things that would be too easy to verify. They have to have those things match up. But yeah, in every other respect, as per usual, they're using mathematics as a replacement for reality, of course. Exactly,
and they're using that 5-degree inclination or declination of the moon's angle to say the moon is high on the Tropic of Cancer or low on the Tropic of Capricorn. When we know in reality, it's because it's closest to the observer, that's why it'll appear higher, just like all objects, you know what I mean? We know that from the laws of perspective.
Well, I mean, the moon is a topic of great interest to most flat earthers, and I mean, I'm more than okay admitting that I don't know what it is that I don't. You know, I'm leaning toward it being certainly some kind of projection.
Yeah, exactly. Like I say, I've been saying it's people laughed at me about a year and a half ago when I said it, the moon was a projection. I put a post on saying, is the moon a projection? And people were like basically ridiculing me and laughing at me, you know what I mean? And
yeah,
like I say, it's coming to light now, and I know a lot of people like Sirius and Chris Monk, they I think they're on the same page as well. As part of my video, what I'm doing, I'm going to do like a time lapse of me on the computer, like doing gathering all the data, you know what I mean, as part of the video, which is
nice.
quite fun. So yeah, but like I say, that's where I'm at with that. And like I say, I've the last 8 months observing the moon, and these observations here, these are just a handful of observations. If you look onto my lunar page, or if you look at my actual phone, where I'm constantly, if I see the moon, I'll take a snapshot and I'll compare it with time and date moon card to see if my readings are matching up with theirs, you know what I mean? And I've got hundreds and hundreds of readings, yeah. What back that up? So it's not just these 2 observations here. I've been doing it on a regular basis, you know what I mean? All these observations here. If you take this one, look on there where it's 144 and 48. I don't know if I click on the right one here. Yeah, and just to give you a little idea, look, there's my reading, my final reading there. It was the azimuth was 144 and the angle was 48. Now, if you go to my actual reading with Dioptra, what you'll see is, yeah, 144, a little fraction out, but not far, and 48. It's not easy to get the moon in the middle of it. You just move a millimeter and it's gone. Like it's
sure.
It's dead hard to get in there. But all them readings match up with the readings from MoonCalc, and when the moon's speeding up on my screen, it's matching up with that meridian passing on time and date. I've got 2 valid mainstream resources here. What my observations are matching up with. You know what I mean? I think that's if you think about Kepler's law of planetary motion, all his laws on planetary motion were based on observations that he pinched, or well, he said he borrowed from his mentor, or well, I think more like a rival, Tycho Brahe. And remember, this was back in the 1600s. All planets travel around in an elliptical orbit. That includes the moon traveling around the Earth. Now, all Tycho Brahe's observations were drawings on pieces of paper. You know what I mean? They weren't real observations. So all his laws were built up from drawings. You know what I mean?
Yeah.
I'm shooting reality, and I'm building my observations on, and I'm matching it up with what's happening in reality. And there's one thing you can't hide, and that's that meridian passing. When that moon is at 180 degrees south, if you pointed your app towards that and it said 270 degrees west, then the questions asked, wouldn't they? So the meridian passing, it can't be hidden. And I've just put 2 and 2 together and started measuring that time between meridian passings to build up my data to back up my claims.